Hi there, this is a tutorial on the uniform continuity of the Fourier transform in two parts. This is part one. The papers are on my website, which is listed here, and what I want to do is basically go through a classical proof of the uniform continuity of the Fourier transform. So it's quite detailed, and you need to sort of follow the this tutorial or go to the paper to really get the best out of it. As a motivation, let's start with a classic signal from electrical engineering, which is this box function here. It's just 1 on the interval minus a half to a half. When we take the Fourier transform of this, something miraculous happens. Notwithstanding the discontinuities here and here, we get this continuous function, and it's actually more than continuous, it's uniformly continuous, and this is the sinc function. So you go from this discontinuous phenomenon here to this uniformly continuous phenomenon. So this is quite a powerful result. What's even more astonishing at one level is that you can go back from here to here with Fourier inversion, and you keep the discontinuities. Now that's tricky to prove. Requires complex analysis, contour, integration, and the residue theorem to prove it, but you can do it. Quite a remarkable result. The fundamental theorem that we need to establish is this. If you've got this Riemann integrable function that's Riemann integrable on every interval a to b, and its absolute value converges, then we can confidently assert that the Fourier transform is uniformly continuous. So that's what we want to prove with those assumptions. And as you can see here, this is the way I've defined the Fourier transform. So we need a definition of uniform continuity, which if you're watching this, you'll probably be aware of. It's all the usual epsilon and delta spaghetti, so it's worth going over. And the logic of the quantifiers is really important, because what it says is that for every positive epsilon you choose, and for every xi and eta in a set X, you can find a delta such that this quantity here is small whenever xi and eta are within delta apart. So it's a global property rather than a local property, because we're looking at a set here, what's happening in a set rather than at a point. If we compare this with continuity at a point, what that says is that you take your epsilon greater than 0, then you come up with a delta such that the difference between these two things is small whenever the distance between x and x naught, the point at which you're doing the evaluation, is within delta of each other. So this is the local property, this continuity here, whereas uniform continuity, because it's talking about essentially the behaviour over a set, it's a much stronger property. So we can see how this works with a brutally simple example of fx equals x squared. And you might think, well, could this be uniformly continuous? Well, we just take 2 points. We let x equals n and y equals n plus 1. N's any natural number. So those two will be close when n's large. We just do the difference. You just expand that. You get that. That's always greater than 2. So f cannot be uniformly continuous, because we could take epsilon equal to 1. Remember, the definition is any epsilon, so take 1, and you can never make this difference less than 1. So it's not uniformly continuous. So when you're approaching these proofs of uniform continuity where you've got integrals, you've got to ultimately get down to this difference being less than some constant times this thing here, because this is the thing that governs the closeness of the points. Because if we get something of this form here, if we can make this if we can make this xi minus eta less than delta, which is less than epsilon on this constant k, k is this constant up here, then what we'll have is that this difference is less than k times epsilon on k, which is epsilon. And that's what we wanted to achieve. So that's where you sort of try to go. And in order to achieve that, what you do is you break the domain of integration up into three parts. And these are the tails, 1 and 2 are the tails, and then the third is the hump, which is this area here. And you've got to use different properties of the function to get the relevant estimates for each of these parts sufficiently small. So ultimately we're going to be looking at integrals of this form. Other definitions are used, and you just need to be aware of that. You can have different factors. You can have a minus pi I there, etc. You can have prefactors out the front. I won't go into that, but you just have to be aware that there are other definitions. So one point to really be clear about is that when you break up the domain of integration, the choices for the point at which you break it up will depend on how big epsilon is. So if you want to make epsilon really small, depending on the nature of the function, you may have to go a long way out. For instance, if you had something that had fat tails that went way up like this and only came down right at the very end, you'd have to move d of epsilon further out. But what we are assured of, because of the hypotheses in the theorem, is that we can find a d of epsilon such that the tails, now this captures both tails, it captures t greater than positive d epsilon, and then the t's less than negative d epsilon. So we can be sure we can get a d epsilon that will make this absolute value, absolute integral, less than epsilon on 4. Why can we do that? Well, we know this converges. So the sequence of partial sums is a Cauchy sequence, and hence we can find a big N such that the difference between those partial sums is less than epsilon on 4 for all m and n greater than this n. That's what convergence implies, Cauchy, and that's where that comes from. So if you have a convergent series, for instance, like if you want an analogy, like 1 on k squared, we know that's pi squared on 6, then we can find an n such that this amount here, this tail, is less than 1 in 1,000. Because what we do is we dominate that series by this quantity here, and when we do that integral, we find that n equals 1,000 work, and so when we plug it in, we'll find that that tail is indeed less than 1 in 1,000, 0.001. When you're dealing with series, we know that convergence of this series implies that the terms tail off to 0, but with integrals, that's not the case, because you can get this integral converging. This can exist, so the partial sums converge, but this thing here does not necessarily tend to 0 as x goes to plus or minus infinity, because you can construct examples where that doesn't work. But we can say with our hand on our heart that this is true. So this is an important bound we need to make this work. We then look at this difference. So we just plug in the Fourier transforms. We just take the value of the function out, the common factor out the front. We then do the splitting up of the integral into the tails and the hump. It's just these two parts here. And then all we do is we use the triangle inequality and the normal properties of pushing absolute values through integrals. And for the tails, what we get is this bit here, this exponential term, we use the triangle inequality on that, and that's less than or equal to 2. And then this is what we get for the tails. We get that the tails just come down to that. So that's 2 times epsilon and 4. So we've done with the tails. The next thing is the hump. We've got to do something with the hump. And this is a bit more subtle. And this is typical of these type of estimates in Fourier theory. So what we've got is this. We know that f is integrable on any interval, hence it's bounded. That's just standard theory. So we can get a number that's going to depend on epsilon. All these numbers are going to depend on epsilon because, you know, the smaller that you make the epsilon, the different you're going to be in a different situation for determining the behaviour of the function. Being bounded means that on this interval in particular, the absolute value of f of t is less than or equal to b of epsilon because it's integrable on every interval and it's bounded on every interval, hence we'll choose this interval. And that's the bound. Now the trick here is we've got to massage this exponential term because remember we want to get something that's just xi minus eta. And the way to do that is to use this little inequality here. And all we do is just simply write out this here in terms of causes and sines. That's easy to do. It's just cos A plus I sine A plus minus cos B minus I sine B. And we just work out the modulus of that. Just a bit of algebra there, nothing hard about that. And we get down to here, to 1 minus cos A minus B. Use the half angle formula to get here, half angle formula. And clearly this thing here can be negative as well as positive, and hence it will certainly be less than or equal to the absolute value. And we know that the absolute value of sine x is always less than or equal to x. If you don't follow that, just draw a little diagram and you'll see why. That's y equals x, and that's sine x there. And of course when you take the positive values it's all symmetrical. So we get this. We just plug in our values of A and B. We get this here. This is A, this is B. Remember that mod x equals minus. So it doesn't matter about, you know, that's a positive eta and that's a negative xi. So what we've found is that exponential term comes down to this, is bounded by that, or the supremum of that over this interval. So that's what we're looking at. This is bounded by the supremum of this quantity here. And the supremum over that interval involves t. If you go back here, there's a t here. The supremum of that over this interval is 2d epsilon. That's where the 2d epsilon comes from. This is just a number that doesn't depend on t. So the hump is dominated by 2 pi times 2d epsilon times b of epsilon times this quantity here, dt. So you've just got a bunch of numbers here. These are just numbers. They're not dependent on t. There's no t dependency. So we can bring all out the front. And it's just the integral of dt over this interval here, which is 2 d epsilon. So this gives us in total 8 pi d squared epsilon, b epsilon, eta xi minus eta. So when we put it all together, this is from the tails, tails, and this is from the hump. So we get that. That's what we get. So we've got something that's looking pretty damn good because we've got this quantity here. And so all we have to do is choose xi minus d minus eta less than or equal to, delta, which is less than epsilon over this quantity here. Because when we make xi minus eta this small, we'll have epsilon on 2 there, we'll have 8 pi, we'll have this over that, and that quantity is less than epsilon on 2, so the sum of them is going to be less than epsilon, which is what we wanted to achieve. So this is our magic delta. You choose delta less than this quantity here. And as you've seen by going through that proof, for any given function, you should be able to constructively demonstrate what this number d epsilon is and what the b epsilon is for any given function. So it's an interesting little exercise to actually pick a function and do that. Take something which, and you could take any function that you feel comfortable with, and then just follow the process through, and that gives you a constructive proof. So that's why that box function turns out to be the sinc function, and it's uniformly continuous. To prove uniform continuity of sine x over x is more tricky at one level, just approaching it from first principles, and you can look at the paper referenced in the written paper on the site to see how that might be done. Anyway, that's enough for part 1, and in part 2 I'll deal with some other issues. Thanks for viewing.